Welcome back to another exciting Physics 11 video. Yeehaw! Today we are going to look at projectiles. So projectiles, we're talking about sort of like throwing objects sideways. One thing that we're going to have to get used to doing, and it might take you a couple of examples before your brain is able to do this, is you're going to have to think about the motion of an object traveling sort of sideways, like throwing a ball maybe, as two separate motions. We're going to look at things that do sort of like parabola shapes as they fall, because they're moving sideways and down at the same time. But in our heads, we really have to keep that motion separate. We want to think about what is the object doing vertically, and then what is the object doing horizontally. And we have to let go of the notion of things sort of falling at an angle. And we want to think about just what's happening in the up and down direction and totally separately from what's happening in the side to side. So I have a little question for you here. There we go. We're going to have somebody shoot a paintball gun. Nice and safe. That paintball is going to come zooming out of the paintball gun. Notice the thing is totally horizontal. It's going to come zooming out with some good velocity. And safely standing behind that person is going to be another person with just a paintball in their hand. And what we're going to do is we are going to have like a countdown, 3, 2, 1, go. And when we say go, the person is going to pull the trigger on the paintball gun and shoot the paintball horizontally. And the other person behind them is simply going to drop the paintball at the same time, from the same height. And we want to know which one hits the dirt first. So we start our countdown, 3, 2, 1, go. What do you think is going to happen? Which one hits the ground first? And I'll scroll ahead one picture. It turns out they actually hit the ground at exactly the same time. And that throws people off sometimes. They'll say things like, no, that can't be the case. But I want to ask you, what's the same for both of those paintballs? And the answer is gravity. Gravity doesn't care if you're moving sideways. It really doesn't. It's going to pull everything down in the absence of air friction at 9.8 meters per second squared. And since these things were both dropped from the same height, gravity pulls down on them at the same rate. They both hit the ground at the same time. And just as proof, here's a photo, something like you might do in a first-year physics class in university. There it is. There's a photo of a ball falling off of, there's a little ramp up here in the corner. There's a photo of a ball that was given some sideways velocity and it's falling, as opposed to one that was just dropped. And you can see that was a picture taken with a strobe light and a camera. You can see that both of those balls are always exactly at the same height. They are falling at the same rate because gravity doesn't care about sideways motion. So they're actually going to hit the ground at exactly the same time. And that's the kind of separation we're going to have to make in our brains when we look at projectiles. This whole thing about what's happening up and down with gravity, and then what might be happening side to side with some velocity. So let's try out an example here. What we're asked to find in this example is the range of the ball. What the range means in a physics sense is the horizontal distance the object travels. So this is going to be the range, just like that. And what we're going to need to do in order to find the range of this object is make a 2-column VIF-DAT list. So these questions are kinematics with a twist where we have to make 2 columns. So I'm going to make my VIF-DAT list here. But what we're going to do, what we have to do with projectiles, is think about the vertical information separately from the horizontal information. Now, here's what we can do with any projectile question that we see in today's lesson, regardless of what the numbers are in the question. I could ask you something like, what's always true for this ball? And you could say, well, I know vertically the acceleration is negative 9.8. We're back to using a negative here. So that's always going to be the case. The other thing is that horizontally, the acceleration is 0. And once that ball is sort of free falling through the air, I would just ask you, is there anything pushing the ball to speed it up or anything slowing the ball down? We'll ignore air resistance again. And the answer is no. So the entire time that ball is falling through the air in the horizontal direction, it is moving at 4.2 meters per second. And since that horizontal acceleration is 0, that means the horizontal VI and VF are actually going to be the same value. It doesn't change. It's just like a horizontal V. It's not actually two separate velocities. The other thing that's the same for both the columns is the time. The object is just airborne for some number of seconds. It can't fall longer vertically than it does horizontally, or vice versa. So that stuff in pink is what you can add to every projectile 2-column VIFDAT list. And now we can go ahead and we can plug in some question-specific values. Like we know vertically this thing is going to fall, so it's negative. It's going to fall 8.4 meters down towards the ground. We know that the horizontal velocity is 4.2 meters per second. Instead of writing it in twice, I'm just going to put it as one big number. 4.2. What we're actually looking for, the end goal for this question, the range, that's the horizontal distance the ball travels. And there's one other number we know. It's implied in this question, and that's actually the vertical initial velocity. So I want you to think about, in the vertical direction, what is this thing doing right at the start? And when it gets to the edge of that building or cliff, it's actually not moving. And then it starts falling once it's off the edge. So the vertical VI is 0. That's going to allow us to scratch the vertical VF. You can look at these two columns, hopefully, and recognize that, hey, we've got enough vertical information that we could head to the formula sheet and pick a vertical equation and start solving for time. So vertically, the equation you're going to use is d equals VIT plus 1/2 AT squared. And the good news about projectiles is that is always going to be the vertical equation that you use. Every single time. So you don't even have to go formula hunting on your formula sheet. It's going to be that one right there. And if we plug the values in, remember that a vertical velocity of 0 multiplied by any kind of time is just 0. So if it's okay with you guys, just to avoid silly mistakes, I'd actually like to just lop that term off. I won't even put the multiplication by 0 in there. That's equal to 1/2 times negative 9.8 times t squared. And if we grab our calculator, negative 8.4 divided by, I know already this half of negative 9.8, that comes out at negative 4.9. So I'm just going to speed things along, try to make this video a bit shorter. There's t squared. Then we have to remember to square root. So that gives us an answer of 1.3093. So that's how long that ball is falling for. So we can add that into our list, and it goes in both columns. And now we're getting close. We can move into our horizontal equation. Let me actually, let me see if I can grab this and just move it up. The horizontal equation, since we don't have any acceleration, it's actually a really easy one. We're going to use, like junior science, just d equals v times t. And the good news is that's always going to be your horizontal equation. It never changes. In this case, we know that the velocity was 4.2 meters per second. We're going to multiply by that time that we just found. And that's going to get us the range, the horizontal distance. So I'm just going to use my answer button. Boom, times 4.2, 5.5 meters. That's how far from the base of the building or the cliff this thing lands. Example number 1, done. Okay, let's try example number 2. This one we're looking for the speed of the stunt car. Microsoft Word clip art. The tractor was a little bit easier. And it's driving off of a building, and it's going to just clear 54 meters of flaming debris. I usually would go into this big story about how this is potentially a scenario from a movie like Die Hard. But just to keep this video short, I won't go crazy with that. You'll notice, just to save some time as well, I've got my 2-column VIFDAT list already made up here. Got the numbers plugged in that are numbers we can use in any question. acceleration at negative 9.8 vertically, horizontally no acceleration, horizontal VI and VF the same number, time's going to be the same number. Let's go ahead and put in some question specific values then. This one, the tractor is going to fall 44.1 meters, so that's vertically negative 44.1. This time they've given us the horizontal distance the thing is going to travel, 54 meters. We're actually looking for, the end goal is the speed of the stunt car, and it's moving just horizontally at the top of the building. So I'm looking for horizontal V. And again, vertically, there's a number that's implied. When that tractor gets to the edge of the building, it actually starts with no vertical velocity before it starts falling down. So vertical VI is 0. We're going to scratch VF. That's going to allow us to use the vertical column first, just like we did in the last example. And remember, the vertical equation is always d equals VIT plus 1/2 AT squared. And once again, that vertical VI of 0 means I'm just going to take that term out. I don't want to think that 0 multiplied by some amount of time is actually a value other than 0. So we'll just scratch that. Negative 44.1 is 1/2 of negative 9.8 t squared. Again, half of negative 9.8 is negative 4.9. So divide both sides by negative 4.9 gives you 9. Remember, that's t squared, that's not t. And if we square root that, we're going to get 3 seconds on the nose. 3.0 seconds. So that's how long this tractor is falling for before it hits the ground. 3.0, 3.0. And then we can go to our horizontal equation, which for all projectiles will always be d equals v times t. Nice and easy. This time we know the horizontal d is 54. We're looking for the v. We've got a time of 3. I think that's a nice number, but let me double check it on the calculator. 54 divided by 3. Ah, there you go. 18 meters per second is what you'd want that initial velocity to be for the tractor driving off the edge of the building to just clear the 54 meters of flaming debris down below. And let's try one last example. We'll go with a skiing example. Unfortunately, ski season was cut short for us this year. Here, this one's a little bit different. We've got a skier, looks kind of like the last example actually. We've got a skier that's going to launch themselves off of a cliff. They're going to want to clear 15 meters of boulders down below the cliff. But this time it's the height of the cliff we're looking for. So to speed things along again, I've already got my 2-column VIFDAT list in there. Let's go ahead and plug in the values that are specific to this question. Here it tells us the skier is traveling horizontally at 7.5 meters per second before they go off the cliff. So instead of writing that in twice, I'll just do one big number. They are going to travel 15 meters horizontally. We want to know the height of the cliff, so that's the vertical d is the question this time. And we do know again that the vertical initial velocity, when that skier gets to the edge of the cliff, they're actually not moving vertically yet, so that's 0. This one's a little bit different. We've actually got enough information this time that we can start with the horizontal column. So looking at the horizontal column of our table, the equation we always use is d equals v times t. So we've got 15 meters of horizontal displacement, a horizontal velocity of 7.5. That's an easy division. That's going to give us 2 seconds of air time. So this skier is going to be in the air for 2 seconds exactly. On that vertical side, we're once again going to scratch the vertical VF. We're not concerned about how fast the guy is falling down, or girl is falling down when they hit the snow after they go off the cliff. So moving into the vertical equation, which is always the same, d equals VIT plus 1/2 AT squared. And one more time, since that initial velocity is 0, Let's go ahead and cancel that out in the equation for ourselves so we don't make a silly math error. And this one's really nice. We're looking for d and it's isolated already. So it's 1/2 times negative 9.8 times 2 squared. And if we run the numbers, 0.5 times negative 9.8 times 2 squared. 19.6. And it comes out negative. The math is telling you that the skier has gone down 19.6 meters. I don't mind if you leave it as a negative or if you switch it to a positive. It's all good. There you go. One sort of summary note we can make here, something you may have noticed in these three examples. In this example, we were solving for something in the vertical column. That was our end goal. We had to start with the horizontal column. And in the previous examples, we were actually looking for something in the horizontal column as the end goal, which means we had to start in the vertical column. So wherever you put your question mark, you actually are going to need to start with the other column in your VIF.dat list first to solve for time, and then you can move into the column that you're really interested in. So there is the lesson. Let me pull up the homework for you. All right, so here's the chapter outline. We are on box number 5. We're looking at projectiles. So the homework is page 152, numbers 2 through 7, which is this document. In the All Resources folder, you'll find that. It's just a single page on gravity. And again, you're just trying out the 2 through 7. Don't do the other questions quite yet. So give those questions a go. If you have questions about those questions or questions about the lesson, fire me an email or come and chat with me at the next Zoom meeting. Take care, folks.